last part of differentiation is differentiating inverse functions. So instead of having y equals, we're going to have x equals. Now, the method is just do dx by dy to differentiate in terms of y, and then do the reciprocal. Now, this comes from the chain rule. So here, dy by dx equals dy by du times du by dx. Now, if I let x equal y, and then u equal x, we get dy by dy equals dy by dx times dx by dy. So we have that. This bit here is just 1. So to get dy by dx by itself, I'll just do 1 divided by dx by dy. Yeah, it's probably just a bit easier to remember, differentiate it and then flip it. So the first one here, if y equals a to the power x, then we want to show that dy by dx is a to the power x ln a. Now, this is an important thing, so I'll try and remember it anyway. Now, you'll know that if y is e to the x, dy by dx is just e to the x. And that works because, look, if a is e, if I put e in there, ln e is just 1. So I just get e to the x. Okay, there's 2 ways of showing this. So method 1 is when we use this new method here. So I'll do that one first. So what we do is we do ln on both sides. So ln y equals ln a to the x. We can bring the x to the front. We can then differentiate both sides. I can divide by ln a first. So ln y over ln a equals x. I can differentiate both sides to get dx by dy. Well, this here just means ln y times 1 over ln a. So I'm going to put the 1 over ln a at the front. And I'm going to differentiate ln y, and that's going to give me 1 over y, remember? So dx by dy is that. So I can simplify that to give me dx by dy is 1 over y ln a. So when I flip both sides, look, dy by dx is y ln a over 1. Then just sub back in what y was, look. So dy by dx, it's a to the x ln a. Yeah, in method 2, when we don't need to use this new method, but we do need to use a to the x equals e x ln a. We do need to use this formula for it. So I'm going to write y as e to x ln a. And just remember, ln a is just a number. So when I differentiate, remember, e just is the same. But I have to times it by the derivative of the power of this thing here. Well, if I differentiate 2x, I just get 2. 3x, I just get 3. So ln a is just a number. So ln a x differentiated just gives me ln a. And I'm going to just change this back into a to the x to get dy by dx a to the x times ln a. Yeah, I think that way is probably a bit nicer. Okay, but it does let us now differentiate some inverse trig. So here we've got y equals arc sine x. You have to show that dy by dx equals this fraction here. See if I can make that a bit clearer. No, that's as best as I'm going to get. So we've got y equals arc sine x. So our first method is going to be get rid of this arc sine. So if I do sine on both sides, I get sine y, and sine and arc sine will cancel out. So I just get that. Now I can't get dy by dx in one go, so instead I'm going to get dx by dy. So this side, when I differentiate it by y, sine goes to cos. So I've got cos y. Okay, I can now flip both sides to get dy by dx is 1 over cos y. Okay, now the trick here is I want to get back to x's. So I look at what y is. So y is arc sine x. It's got something to do with sine. I've got cos, so I have to think what formula links cos and sine. So I have sine squared x plus, actually I'm going to use y because I've got cos y here and sine y there. So cos squared y and sine squared y, when I add them together, I get 1. I want cos y, so I'm going to rearrange it to get cos squared y, 1 minus sine squared y. So cos y is root 1 minus sine squared y. Remember, I can't square root individually. Now, sine y here is just x. So sine squared y is just x squared. So cos y is root 1 minus x squared. And that's tricky. That last step there, spun that. It's tricky. So sine y is x. So sine squared y is just x squared. And put that back into there. So we get dy by dx is 1 over root 1 minus x squared. And that's how we get that result there. There are some more simple applications, which will be the last example we're going to do, which is if I've got a curve given by x equals rather than y equals, then we can get gradients and normals and tangents and all that much quicker. So find the gradient of the curve x equals y squared plus 5 at the point 6, 1. So I could use my old method. I could rearrange it to get y equals x minus 5 square rooted. I can then differentiate that. So that's x minus 5 to the half. I can differentiate that to dy by dx is a half, take away 1 to the power, times by the derivative, which is just 1, and then sub in the x, which is 6. So dy by dx is 1 over 2, 6 minus 5 to the minus half. That just gives me a half. Yeah, with the new method, this way hopefully you're going to see much quicker and a lot nicer, less likely to make mistakes. The new method, and there's nothing wrong with doing this, by the way, if you get the new method. The new method, I've got x equals only 1x, so straight away let's just get dx by dy. So dx by dy, y squared differentiates to 2y, plus 5 disappears. So flip both sides, so dy by dx is 1 over 2y. We know y is 1, so sub in y is 1 to get dx by dy. Sorry, dy by dx is 1 over 2. That's it, much quicker. Yeah, but whichever way you prefer, you use that way.